The chapter rotation is now complete, and so I have come up with previously here asked questions. This will help you to assess what is your level of preparation. So let us get started. Let us start with the first question. A circular disc of radius b has a hole of radius a at its center. If the mass per unit area of disc varies as ρ0 upon r. Here you can see mass per unit area, that is areal density, is varying as inverse of the distance from center. Then the radius of gyration of disc about its axis passing through the center is. It is asking for radius of gyration. So let us start solving this. See, we know very well we can write radius of gyration as, because we know I can be written as mk square. So k from here can be written as root under I by m. If we know value of moment of inertia about the center, then we can write value of radius of gyration very well. So let us first calculate mass and then moment of inertia, and then we can substitute in the formula given here. So let us start with calculation of mass. Let us first consider the given disc for which inner and outer radii are provided. Now let us consider one elemental ring which is having radius r and thickness dr. So if I write mass of this elemental ring, dm can be written as, it should be mass per unit area into area of this elemental ring. That will be equal to sigma naught upon r into area of ring has to be equal to 2 pi r dr. Now to get mass of the remaining part, we can directly integrate this value. Sigma naught upon r into 2 pi r dr, and this integration has to be within limits a to b. So that will give the final result sigma naught 2 pi b minus a, which is mass of the remaining cut disc. Now we have to calculate moment of inertia. So let us calculate the value. Again we can consider the same elemental ring, write its moment of inertia about the center, and then integrate it to get moment of inertia for the whole shape. So I can be written as integration of r square dm. dm already we have calculated, so the value directly can be put here. That will be r square sigma naught upon r into 2 pi r dr. It has to be integrated from a to b. On substituting all the values and integrating, the answer will come out to be sigma naught 2 pi. This is r cube upon 3 within limits a to b. That will be equal to 1 by 3 sigma naught 2 pi. It has to be b cube minus a cube inside the bracket. Now we can directly substitute in the formula of radius of gyration, that will be equal to I by m. So it has to be sigma naught 2 pi b cube minus a cube upon 3 sigma naught 2 pi b minus a. This 2 pi term got cancelled, sigma not cancelled. So the final result will be under root 1 by 3 b cube minus a cube upon b minus a, which is our option number C. Let's move to the next question. A stationary horizontal disc is free to rotate about its axis. When a torque is applied on it, its kinetic energy as a function of theta, where theta is the angle by which it has rotated, is given as k theta square. If its moment of inertia is I, then the angular acceleration of the disc is. Here we have to write kinetic energy of the rotating body. As we know, kinetic energy can be written as, it should be half I omega square. So if this is to be equated by k theta square, which is given in the question, Let us write this value to be equal to k theta square. From here we will get omega square to be equal to 2k theta square upon I, which gives omega as root under 2k by I into theta. Now we have to calculate angular acceleration. So let us differentiate this omega term we have just obtained, and angular acceleration alpha can be written as d omega by dt. So if we integrate this expression with respect to time, it will give root under 2k by I being constant can be written like it is, and then d theta by dt, which is equal to root under 2k by I multiplied with omega. And already we have value of omega here. So if we substitute this, it becomes root under 2k by I. In place of omega, it can be written theta into root 2k by I. So the final answer will be 2k by I multiplied with theta, which is our option number D. Come to the next question. A thin circular plate of mass m and radius r has its density varying as ρ0 r, with ρ0 as constant and r is distance from the center. The moment of inertia of circular plate about an axis perpendicular to the plate and passing through its edge is I, which is alpha mr square. The value of the coefficient alpha is, we have to calculate value of this alpha here. So let us start doing the question. Again, since it is a circular plate and density is varying, so we have to consider one elemental ring. Let us consider that elemental ring for which the radius is x and its thickness is dx. For the whole disk, radius is given as r. Now moment of inertia of this ring about the perpendicular axis which is passing through the center can be written as di is equal to, it can be written as dm into x square, because for the elemental ring x is its radius. Now if I substitute value of density, then dm can be written as density multiplied with area of the ring, that has to be 2 pi x dx, and then multiplied with x square. So on solving it, we will get 2 pi ρ0 x to the power 4 dx. Now if we have to get moment of inertia of this elementary ring about a perpendicular axis which is passing through the edge, then we have to apply parallel axis theorem. So di dashed can be written as, because here we have to calculate mi about an axis that is perpendicular to the plate and passing through its edge. So di dashed can be written as dmx square, already we have calculated, plus dmr square. So that this value will be equal to 2 pi ρ0 x4 dx plus 2 pi ρ0 r square x square dx. Now we can get for the whole plate moment of inertia which is desired here. So alpha mr square can be written as equal to integration of this di dashed. So that will be equal to integration of 2 pi ρ0 x4 dx, limit has to be from 0 to r, plus integration of 2 pi ρ0 r square x square dx, and again integration from 0 to r. On integrating these two terms, final we will get as 16 upon 15 pi ρ0 r5. So if we equate this with alpha mr square, now to equate this with alpha mr square, first we have to get value of m, then only we can substitute the value here. So let us calculate mass of the ring separately, that can be written as integration of dm, and which is given m, So it has to be equal to, first I am writing mass of the elemental ring, that will be equal to sigma naught r into 2 pi r dr, and this has to be integrated within limits 0 to capital R. So on substituting, it will be 2 pi rho naught taken outside the integration. Now this becomes integration of r square dr, that will be r cube upon 3. So this is value of m. If I substitute value of m on left hand side, that will give alpha r square into 2 pi rho naught upon 3 r cube. From here this r5 got cancelled, rho naught got cancelled, pi got cancelled, this is 5, this also is 8, and we got value of alpha to be equal to 8 by 5, which is our option number 3. The next question is, the time dependence of the position of a particle of mass m is equal to 2 is given by, r is given here, that is 2ti minus 3t square j. Its angular momentum with respect to the origin at time t is equal to 2 is. Now first we have to get value of velocity, because to write angular momentum L, it has to be r cross mv. So first we have to get value of velocity and then we can calculate it. So let us write velocity should be equal to dr by dt. On differentiating it, this will come out to be 2i minus 6tj. This is the value of velocity given. Now it is asking for time t is equal to 2 seconds. So at t is equal to 2 seconds, both the values can be written, that will be r2, its value has to be 4i minus 12j, and velocity at t is equal to 2 seconds will be 2i minus 12j. So these are the values of position vector and velocity at t is equal to 2 seconds. And then finally we can write L to be equal to, it has to be r, which is 4i minus 12j cross mv. M is given here 2, so just multiply this whole velocity term with 2, it will be 4i minus 24j. Now on taking the cross product, we will get minus 48k, which is our option number 3. Next question. A particle of mass 20 gram is released with an initial velocity 5 meter per second along the curve from point A. As shown here, the point A is at height h from point B and the particle slides along the frictionless surface. When particle reaches point B, which you can see here, it is the lowermost point, its angular momentum about O will be. We have to calculate angular momentum about this point when the particle has reached at the lowermost point. So let us see how this can be done. Friction is absent, so we can write that energy at A has to be equal to energy at B. Now what is energy at A? That can be written as half mVA square plus mgh. This should be equal to half mVB square. And from here we can write VA square plus 2GH to be equal to VB square. On substituting all the values, VB square will be equal to 5 square plus 2 into 10 into 10, which is 225. So we can write VB to be equal to 15 meter per second. We got the speed at lowermost point. Now we have to write angular momentum. So angular momentum directly can be written about O, as here the velocity must be horizontal. So about O we can directly write angular momentum to be equal to mVB into RB, where RB is perpendicular position from the O to point B. This will be equal to 20 into 10 to the power minus 3 into 15 into 20, which is 6 kg meter square per second, which is our option number 4. Proceed to next now. A disk of mass m and radius r is rolling with angular speed omega on a horizontal plane as shown. The magnitude of angular momentum of disk about the origin is. Now see, from the theorem we can write L about O to be equal to L about center of mass plus m r cross v. In last session, I had explained this, how angular moment of an object can be calculated if its axis is not constant. So, now I am going to apply this formula. This LCM can be written as, it has to be I omega, because with respect to center of mass, the body is in pure rotation. So, directly we can write the value to be equal to I omega. Now, this is a disk. So, I will be mr square by 2. And then LCM we got as mr square by 2 multiplied with omega. The next term is mrv. That will be equal to, only here I am interested in its magnitude. So, directly it can be written as mr and then v can be written as omega r. So, this value will be equal to mr square omega. And from here we can get magnitude of LO to be equal to, it has to be mr square omega plus mr square by 2 omega. And so the correct option will be 3 by 2 mr square omega, which is our option number 3. A solid sphere and solid cylinder of identical radii approach an incline with the same linear velocity. Both roll without slipping throughout. The two climb maximum heights h for sphere and h for cylinder on the incline. Then we have to calculate ratio of these two heights. Okay, let us start with the kinetic energy, because kinetic energy can be written as, it should be kinetic energy due to translation plus kinetic energy due to rotation. So, mathematically it will be equal to half mv square plus half I omega square. Here the term is rolling. So, it has to be both the translation and rotation involved. Now, if I write the values for k, that should be equal to half mv square plus half I omega can be written as it is a pure rolling. So, this has to be v square upon r square, where v is linear velocity and r is radius for both sphere and the cylinder. And so, we can write kinetic energy for sphere to be equal to, this should be half mv square plus half, now I for sphere has to be equal to 2 by 5 mr square. So, this is 2 by 5 mr square into v square upon r square. These two got cancelled. The result will be equal to 7 by 10 mv square. Similarly, we can write kinetic energy for solid cylinder as well. So, it has to be K for cylinder. If I write, that will be half mv square plus half. Now, for cylinder, the term I has to be equal to 1 by 2 mr square. So, this is mr square by 2 into v square upon r square. Again, these two got cancelled and the final result is 3 by 4 mv square. Now, from energy conservation, we can write mgh to be equal to kinetic energy. So, for both the objects, that is for sphere and for cylinder, we can directly write h of sphere upon h of cylinder to be equal to ratio of their kinetic energies, which is 7 by 10 into 4 by 3. That will be equal to 28 upon 30, which is 14 upon 15. And the correct option is option number 2. The next question is, a string is wound around a hollow cylinder of mass 5 kg and radius 0.5 meter. If the string is now pulled with a horizontal force of 40 Newton, as you can see here in the diagram, the cylinder is rolling without slipping on a horizontal surface. Then angular acceleration of the cylinder will be, here m is given 5 kg, r is given 0.5 meter and horizontal force is 40 Newton. So, if cylinder is rolling without slipping, which is already mentioned here, we can write for the cylinder, let us first draw an FBD. This is the external force F. Here is the center of cylinder. We can write torque about center, that will be equal to, torque can be written as, it has to be F into R, and that should be equal to I alpha. Now as it is a hollow cylinder, so I has to be equal to mr square only. Mr square multiplied with alpha. From here we got mr square alpha being equal to, F is given 40, R is 0.5 meter, so this will be 20. And then we got value of alpha as 20 upon, again mass is given, this is 5, and then square of radius, which is 0.25. The answer will come out to be 16 radian per second square, which is our option number 2. In next question, a disc is rolling without slipping on a horizontal surface. C is its center and Q and P are 2 points equidistant from C. Let VP, VQ and VC be the magnitude of velocities of point P, Q and C. Then we have to find relation between VP, VC and VQ, which one is larger, which one is smaller. So let us think logically over it. As it is pure rolling, so the bottom point, this contact point, should be instantaneous center of rotation, which is known as I core, and it must be having zero velocity. Now velocity of any point on the disk can be written as V is equal to omega r, where r has to be its distance from the point O. So if now we check the value of r for each point, for P it is this, for C and then for Q, then we can see that RP is smaller than RC, which in turn is smaller than RQ. So from here we can conclude RP less than RC less than RQ. And as omega has to be same for the whole body, so we can write the same result for velocities as well. So VP should VC less than VQ, which is our option number 1. Where VQ is greater than VC, that in turn is greater than VP. Now the next question is, a constant torque of 1000 Newton meter turns a wheel of moment of inertia 200 kg meter square about an axis through its center. Its angular velocity after 3 seconds is, okay. So first calculate the value of angular acceleration, as torque is given here. So we can write torque is equal to I alpha. Now alpha can be written as torque upon moment of inertia. Torque is 1000 provided and moment of inertia is given 200. So this is equal to 5 radian per second square. Now we have to calculate angular velocity after 3 seconds. This can be calculated using the kinematical relation omega is equal to omega naught plus alpha t. As initially it was at rest, so omega naught can be written as 0 and then omega will be alpha multiplied with t, which is 5 into 3, that is 15 radian per second. So the correct option is option number 4. The next question is, a wheel of radius 1 meter rolls forward half a revolution on a horizontal ground. The magnitude of displacement of point of the wheel initially in contact with the ground is. If I draw this situation which is given in the question, it is the lowermost point, and since the wheel has been rotated by angle pi, so this point must come to here at the uppermost point. So this is P1, this is P2. Now we have to get its displacement. As center of mass for half revolution has to move by pi r, so this distance between their centers can be written as pi r, and from here, as this is 2r, we can get value of P1, P2 to be equal to, this should be under root 4r square plus pi square r square. But r is given 1 meter here, so it has to be 4 plus pi square, which is our option number 4. With this, now our whole chapter rotation is complete along with the previously year asked questions. Now I hope you understood all the concepts and have solved a number of questions. Keep practicing. Goodbye.